All right, so now we're going to turn our attention to how capacitors behave when they are in circuits, either in series or in parallel. The mathematical relationship for series capacitors is actually similar in mathematical treatment to the resistors in parallel treatment. The capacitors all receive the same amount of charge. The current is the same that's flowing through those. And then the actual value of the voltage is dependent upon the amount of charge that is stored on those capacitors. We can see here that the net capacitance in a series circuit does have an inverse relationship in the way that the resistors do in parallel. For parallel capacitors, the relationship is simpler. It's just the way that you mathematically added up series resistors. So in parallel, what we do is we just add the values of the capacitors to find the total net value of capacitance in that circuit. All right, so let's actually do a capacitor network problem so that we can exercise this knowledge. All right, so here we have our capacitors, and yes, I picked friendly numbers like 470 microfarad. So there's a little bit of heavy lifting from just a punch the numbers into your calculator perspective. But let's break this problem down before we go for the total capacitive value. If we look at this particular capacitive network, we see that we have a combination of both series and parallel capacitors. So let's check out which ones are the parallel capacitors. We've got a group here that are in parallel and a group here. And because the easy thing, or capacitors are actually easier on the parallel side, we just get to add them. So I'm going to write up here for easy reference what the capacitive value is for that network that's below. This is the sum of these three, and that's 1440 microfarads. Here we just carry the existing number. Here it's going to be 940 microfarads, and then we have 470. Now, if I look at this, this is just a set of 5 series capacitors. I'm just drawing a quick view of that circuit, or that resistor network, or excuse me, capacitor network. And so I've got 5 in series, and then that's the case where I get 1 over C equivalent is equal to 1 over 470, and all of these are microfarads. And I'm going to have that 3 times, so I'm just going to go ahead and represent that as 3, since I have 3 of those, plus 1 over 1440 microfarads, or 10 to the minus 6, plus 1 over 940 times 10 to the minus 6. And then all those together, this 1 over CEQ. So you have to pull out your calculator to do this. These are approximate numbers. I'm not carrying all the digits. And that's equal to 8155, and that's over the units of farads. So what we get if we invert that to figure out what CQ is, we get 123 microfarads. So inverting this to get CEQ. So this is the net capacitive value of this network. This network, then we modified it to look, or to mathematically be represented this way. And then we used our formula for the series capacitors, and our total capacitance comes out to be CEQ equal to 123 microfarads. All right, so that's pretty straightforward, and it's similar to what we've done in the past. Of course, I'll now let you exercise this knowledge in doing this capacitor problem. So the goal is to find out what the net capacitance is, or the total capacitance is at this point. So your approach will be to break down what's a series, what are capacitors in series, and what are capacitors in parallel. And I'll come back with the answer for that, but I'll give you a few minutes to work on it. With regard to inductors, we'll again look at their series and parallel behavior, and they are very similar in the way that we mathematically consider resistors. So inductors, we get to add the inductor values. For parallel, we get to treat them in the same inverse relationship that we did for resistors. So these formulas should look straightforward to you. Here is a simple circuit or a network showing us a set of inductors, and the formula for this is that you just add up the inductance values in a series situation. In a parallel network, it's just the same behavior that you do with resistors. It's 1 over LP is the parallel value or the net inductive value for this circuit. So it's 1 over L1, 1 over L2, 1 over L3, and so forth out to the full set of parallel inductors in that network. All right, so as you can guess, we're going to do an inductor example to leverage our newfound knowledge. All right, so what do we have here? We have a circuit, or we have a network, and it's going to make it a little bit easier simply because because I've shown you inductors that have 5 millihenry values, and they're all 5 millihenry values. So let's consider what this circuit is and where we have series and parallel. So the first one I'm going to do is I'm just going to go over here and pick up these two parallel. So L1 is going to equal to, which gives me that L1 is equal to 2.5 millihenries. All right, so that, if I can collapse these down into one that's equal to 2.5 millihenries, and that should be what you would expect based on a lot of times where we've done the series resistors. All right, so I'm going to redraw this circuit or this network just to highlight so that we can clearly see what's in series and what's in parallel. So if I start out down here, so I'm going to start, this is my starting point, and then I'm going to go here. Now what do I have here? I've got two inductors that are in series. So that means if I come from that end of the circuit, I'm going to see 10 millihenries here. Now what I have is a 5 and a 2.5. And what are they in how are they arranged? They are arranged in parallel. So I have 2.5 and I have 5. So that's capturing this network. And then what do I have over here? I have another 5 millihenries. All right, so then what I'm going to get is LEQ is equal to 10 plus 5 times 2.5. If you'll recall, when I just have two resistors, it's similar to what happens if you just have two inductors. So you can actually multiply the two values and then divide by the sum. So that's actually what I'm representing here. And that's going to give me 16.67 millihenries. So LEQ, which is this, or the net value of the network, is here. All right, so that's a pretty straightforward network for us to work through. All right, so here's problem 10. And this network, so the first thing to, of course, think about is what's in series, what's in parallel, how can you start to simplify that network, and then move through that simplification process to actually get the desired LEQ. All right, and I'll come back with that answer. All right, so one thing that I recommend is that you take a few moments and review every circuit simulation that I have given you links to. Those circuit simulations give you a very good overview of all the capacitance and inductance behaviors that we've talked about today. So take a few moments and look through those to just reinforce the knowledge that we've gained thus far.